Hi, I'm Dr. Matthew Michal. I'm a lecturer at NJIT. I teach mathematics. Today I'm going to be talking about homogeneous equations, well, more specifically about second-order differential equations and how they involve the homogeneous problem. So now we're talking about Chapter 3. So in Chapter 3, we're talking about second-order linear, frequently homogeneous, but second-order linear differential equations. Now a second-order differential equation, if you notice on top, is talking about functions, differential equations, in terms of y double prime, y prime, y, and some independent variable, either t or x frequently. And so f is still my rate function that we saw with a first-order system. Notice below this, we say that it's linear if in front of each one of the y terms, either y double prime, y prime, or just y itself, the most that we can multiply these y's by are a function of that independent variable t or x. Y is not in a function, y is not being divided into something, or the like. If it doesn't follow this form or the form below it, we're going to consider it nonlinear because it doesn't fit that linear format. There are different gradations of linearity, but we're really only going to focus in on the straight-up linear case. That bottom equation, P of t y double prime plus Q of t y prime plus R of t y is equal to capital G of t. This is our kind of general model case. Frequently, we will divide out by that P of t, so we'll have a y double prime by itself, and we'll frequently write the coefficients in lowercase instead. Now today we're going to focus a lot on the homogeneous case. This is the case where we only have y terms. I mean, there might be t or x involved in it, but on the other side, we're not going to have any forcing going on. There's nothing forcing things moving, just the interactions between the different y values. If it does have just a strictly non-y case, like a t or a sine of t or an e to the t, we call this a non-homogeneous problem. Even more so today, we're going to focus on the homogeneous equation with constant coefficients. Lastly, we will consider it with initial conditions. Notice conditions, not just a single condition, because whereas for a first-order system we needed one condition, now with a second-order system we're going to need two. So for a third order, we'd require three. And what we frequently will use will be the initial position and the initial slope, the y0 and the y0 prime. Now let's take a look at this. Now, for this equation, y double prime minus y is equal to 0, we're really asking the question, what functions have the second derivative y double prime equal to the original function itself? So in this case, well, e of t, right? If you take the graph of this function, y is equal to e of t, no matter how many different variables, that's my cat, no matter how many different derivatives I take of that function, it will remain e to the t. So yeah, y double prime does equal to y. Also, y2 is equal to e to the negative t because after two derivatives, a negative times a negative is a positive. So we get the original function back. But also notice that any of those other solutions, y3, y4, y5, adding constants or even adding them together doesn't change the graph itself, doesn't change that these are solutions. So we can put it kind of in this general form, c1 e to the t plus c2 e to the negative t, because any choice of c1 and c2 will make this work. However, if I had instead said, hey, I want a specific interchange of values, then I would actually have to worry about that. I could plug in into that system of equations and get a solution. Plugging in y of 0 is equal to 2 and y prime of 0 is equal to negative 1. Well, if I know y of t's form, which I did in the last slide, I take the derivative and plug in t is equal to 0, I can determine that system. And indeed, 1 half e to the t plus 3 half e to the negative t does indeed satisfy both the initial position and the initial slope conditions. In order to solve these systems in this chapter, we're going to assume the form of an exponential as our solution. This part of what this justification comes from is when we did the first order. Remember, our integrating factor was an exponential that we integrated. So let's say we have an exponential solution, e to the rt. Well, if that's the case, taking the derivative y prime and taking the derivative y double prime gives us r e to the rt and r squared e to the rt respectively. Plugging it into the equation, we actually see that we get this quadratic equation, ar squared plus br plus c. Where a, b, and c are my coefficients of my differential equation. This is known as a characteristic equation. It describes some of the characteristics or key properties of the differential equation. And well, quadratic equation, quadratic formula, we can describe kind of what's going on. For this formula, note that we get 3 really distinct cases when we look at the discriminant, b squared minus 4ac. If I know that b squared is bigger than 4ac, I'm going to get results that are real and distinct, that I'll get a real positive number inside that square root, meaning that that plus and minus will be of a positive real number. So that gives me distinct numbers. The next case is what happens if they're equal to each other. Well, that square root will still work, but now because it's equal to 0, my r values are the same. They're negative b over 2a. Oftentimes we'll describe this as real and repeated, whereas the first one was real and distinct. Lastly, we have the case where b squared is smaller than 4ac. And in this case, we're taking the square root of a negative number, which means our roots will be imaginary or complex. Idea is that we have some imaginary numbers in there. But for today, let's focus in on the real and distinct case, because that's the easiest to understand. And in this case, we don't even really usually need the quadratic formula in order to determine it, and we can plug it into this nice pretty form. Now, for those of you who do like the formulas, we do have formulas for C1 and C2 that will work every time, but it's usually not worth it. I mean, take a look at this case. Y double prime plus 5y prime plus 6y is equal to 0. Plugging in my assumption, that's what it is, it's just an assumption, e to the rt, into the differential equation, we get r squared plus 5r plus 6 is equal to 0, which is easily factorable, giving us roots of -2 and -3. So therefore, the general solution is c1 e to the -2t plus c2 e to the -3t. If I had initial conditions of y of 0 is equal to 2 and y prime of 0 is equal to 3, these would be known before I started the problem, by the way. Then, by taking the derivative of y, notice below, then I could plug in initial conditions and determine C1 and C2. Now, before I finish this problem, I can also imagine what this might look like. And without even finding the values of C1 and C2, I can predict what this graph is going to look like. See, my initial position is 2, so on the y-axis it has to start at 2. Y prime of 0 is equal to 3 means it's going to have a positive slope moving up. Lastly, in my general solution, both roots are negative, meaning that there's going to be a decay down to 0 regardless of initial condition. And notice it does exactly that. We know that without actually knowing this particular thing. Just make sure to take a look at your conditions and your roots, and you can predict what this is going to look like. Once again, I can predict what this is going to look like. Before I find out the roots, I can easily see that I have, once again, a positive starting off point at 2. But the slope this time is much smaller, but it's still positive. So it's just above flat, just above the 0 line. This one's a little bit harder to factor. It is factorable, but this one might be worth it to use the quadratic formula. It won't be pretty at all, but it is possible, and it might be worth it, depending on who you are. Also notice because the roots are positive in this case, unlike the other one, this means that it's going to diverge, either to positive or negative infinity. So what we need to do is we need to look at the constant of the root related to the bigger root, the constant related to the bigger root. Since that's the 3/2 here, that means I'm going to be paying very close attention to the C1. Because if C1 is positive, it's going to go up to infinity. If C1 is negative, it's going to go down to negative infinity. And notice C1 is negative. Not much, but it's enough to ending this decay. I can also do Calc 1 on this, max, min, and all that jazz. Looks like the max is happening right about 1/2. But as always, remember, a max is just when the slope is equal to 0 and the concavity is negative. So, if we want to find any critical points, find when the slope is equal to 0. Well, that's when t is equal to the natural log of 7/6. Hope this is helpful.